Miss Shalini,
Yes, yes,
We'll
we
start.
can start the program.
Yeah.
oh, thank you. Hello, everyone, and a very good evening to each one of you present with us today. This is L. Shalini, representing Prime Publisher, and I'm glad to welcome you all to the One Day International webinar on the topic Microstrip Antennas and Scattering Parameters. Participants can share their views or ask their questions by posting the same in the comment section at the close of the speech, and our resource person would be glad to interact with you all. The feedback form link will be posted at the close of the session. I'm pleased to introduce our resource person for today's webinar, Mr. K. Prahalada Rao. Mr. Prahlada Rao is a full-time PhD research scholar at Department of Postgraduate Studies and Research in Applied Electronics, Gulbarga University, Gulbarga, Karnataka, India. He has done his Bachelor's of Engineering in Electronics and Communications Engineering from Osmania University, Hyderabad, Telangana, India, and obtained his Master's of Engineering in Microwave and Radar Engineering from RMIT University, Melbourne, Australia. Mr. K. Prahlada Rao has submitted his PhD thesis titled Some Studies on Design and Analysis of Microstrip Antenna Arrays and is waiting his viva voce in Open Defense soon. His areas of research interest include microstrip patch antennas and arrays, electromagnetic band gap structures, defective ground structures, effect of nanomaterials on microstrip antennas and arrays, microwave and radar antennas, radar communication, microwave and RF engineering, electromagnetic theory and transmission lines. He has published several papers in national and international conferences and journals indexed in Scopus, Web of Science, etc. He has also performed the role of reviewer for 6 manuscripts for the following journals: IEEE Access, Scopus Index, International Journal of Electrical and Electronic Engineering and Telecommunications, Scopus Index, Engineering Technology and Applied Science Research, Web of Science Index, Frequent Scopus Index, and Journal of Iranian Association of Electrical and Electronic Engineers. He has also reviewed one manuscript for an international conference. Recently, he has been selected as a member of the reviewer board for the Journal of Mineral, Metal and Material Engineering. Having said this, let me just request our resource person to please take over this session.
Okay. Thank you, madam. Today's topic for the talk is on microstrip antennas and scattering parameters. Next slide, please. Excuse me, madam. Next slide, please.
So are you able to?
Before one, madam. Yeah.
Miss Shalini, can you please maximize your slide?
Yeah, it's in the maximized mode.
No, it is not in the maximized mode.
That is what it shows.
No, actually, yeah, press F5. Yeah.
Is it okay?
Yeah, it's okay.
Okay. Thank you, madam. First, I'll take you through the Okay, today's uh, talk is about the microstrip antennas and scattering parameters. First, I'll take you through the organization of the talk. First, I'll speak about the general introduction. Next, I'll introduce what is a microstrip antennas. Then I'll discuss what are the various feeding mechanisms of microstrip antenna and the radiation mechanism of a microstrip antenna, followed by the pros and cons of microstrip antenna, then the applications of microstrip antenna. Then I'll speak about what is a microstrip antenna array, followed by how do you excite a microstrip antenna array. Next, the latter half of the talk deals with the what are scattering parameters and what are the performance parameters of microstrip antennas and arrays. And I'll wind up my talk with the conclusion. Okay. Next slide, madam. Thank you. First, coming to the introduction, in general terms, communication is defined as like transmission and reception of data or information or some signals between two or more points. Okay, communication is nothing but an act of receiving and sending and receiving messages between two or more entities. Okay, now figure 1 shows the general block diagram of any communication system. Okay, communication system is nothing but a combination of hardware and software units which can perform different tasks. If you can see the first block there, the first block is designated as information source. Okay, information source is the one which generates the information or data in the form. It can be in any form, like it can be either in the electrical form or electronic form, or mechanical form, or in the form of bits. Okay, now the second block, if you can see there, is your input transducer. Okay, a transducer is a device which converts data from one form into another form. Okay, so here we are taking an input transducer which converts data from one particular form into electrical form, because for any communication system to function, input signal needs to be in the form of an electrical form. Okay, so the third block is your transmitter. Transmitter is the one which takes the electrical signals and transmits to the destination. So that is what is the job of your transmitter. That electrical signals need to be sent through some channel. That channel can be either free space or a coaxial cable or anything, but it has to be some channel or some way or some bridge so that the signals can be transmitted. Okay, the next block is your receiver. Receiver does the job of where it can receive the electrical signals that have been transmitted by the transmitter. Okay, the last block is your output transducer. Okay, output transducer converts the data that has been received into the original form, that is form which we have sent it before. So this is the general explanation of a block diagram of a communication system. Okay, you can have various types of communication systems, like a wired communication system, wireless communication. You can have telegraph communication, radio, microwave communication, and radar communications. Next slide, madam. Thank you. Now, what is wireless communication is? Wireless communication is defined as transmission and reception of electromagnetic waves or a signal between two or more points which are not connected by an electrical conductor, which means there is no physical connection between the 2 points. Okay. Next, what is an antenna? Okay, the other terminology for your antenna is also called as your aerial. Okay, antenna is defined as an electrical device or an electronic device which is used to transmit and receive electromagnetic waves. Okay, one thing to be noted here is that an antenna can transmit and receive electromagnetic waves separately, as well as an antenna can transmit and receive electromagnetic waves singly. Okay, whenever an antenna is performing the transmission and reception on its own, that antenna is called as your duplexer. Okay, duplexer is defined as an antenna which can transmit and as well as receive electromagnetic waves. Okay, antenna plays a very key role in the communication system. For example, it can be employed in a resonant circuit. Okay, an antenna can be employed as a matching device. Okay, everybody might be knowing what is a matching. Okay, this terminology you will experience in transmission lines. Okay, where antenna can be used as a matching device means that the input impedance and the output impedance can be matched. That means we are trying to make that impedance equal so that maximum power can be transferred to the output device. Okay, nowadays antenna researchers are concentrating more on different types of antenna because of their prominence in the wireless communication devices and systems. Okay, these antennas play a very important role in various types of communication systems, ranging from cell phones to your GPS navigators, radars, etc. Okay, now you might be seen various types of antennas. Uh, Before, madam. You can might have seen various types of antennas like your Yagi-Uda antenna. Okay, Yagi-Uda antenna is the one that you can see on your terrace, which is used to receive television signals. You also have the dish antenna, you have the rhombic antenna, horn antenna, parabolic reflector. Okay, next slide, madam. Thank you. Okay, now coming to what is a microstrip antenna. These microstrip antennas have nowadays become very serious field of research in among the antenna researchers. Okay, because of their various advantages, like they are very light in weight, possess very low volume. Okay, secondly, they possess planar structure. Third one is they can be easily manufactured and can be easily fabricated. Finally, they can be easily integrated with other electrical devices. Okay, the birth of the microstrip antennas was around somewhere 26 years ago by the work of the scientist called Dishans in USA. But these antennas were practically implemented by the scientist called Munson on rockets, radars, and missiles. The other terminology for microstrip antennas are printed antennas. Okay, why microstrip antennas are called printed antennas? Because they can be easily printed on your printed circuit boards. Printed circuit boards are nothing but that your PCB. Okay. Before slide, madam. Thank you. Okay. Now the very important point is microstrip antenna consists of three major parts. Okay, first is your ground plane, second one is your dielectric substrate, and third one is your radiating patch. Okay. Next slide, madam. Thank you. Now you can see in your figure 2. Figure 2 designates the basic structure of your microstrip antenna. Okay, the gray structure which you are able to see in the form of a rectangle is called as your dielectric substrate. Okay, in your electromagnetic theory, you must have seen that there are two types of materials in your electromagnetics. First one is your conductor, second one is your dielectrics. Okay, that dielectric is nothing but this dielectric substrate. Okay, dielectric substrate or dielectrics are the substances which are bad conductors of electricity, which play the opposite role of your conductors. Okay, the structure that is sitting below the dielectric substrate is your ground plane, which is in the white layer just below the dielectric substrate. This ground plane is a purely metallic structure. Okay, the structure that is sitting on top of your dielectric substrate, which is designated in blue color, is called as your radiating patch. Okay, this radiating patch is responsible for the transmission and reception of your electromagnetic waves of your microstrip antenna. Okay, this is your basic structure of your microstrip antenna. Okay, now the radiating patch can take any desired shape like your rectangle, square, circular, elliptical, pentagon, etc. But generally, antenna researchers use rectangle or square or circular shapes of radiating patch because the general formulae that are employed to determine the dimensions of the radiating patch and the ground plane are available for the only these three shapes. Okay, and next slide, madam. Thank you. Now, coming to the feeding mechanisms of microstrip antenna. Feeding mechanisms means how do you excite or energize a microstrip antenna. Okay, the feeding mechanisms of microstrip antenna can be classified into two categories. First one is your contacting method, and second one is your non-contacting method. In the former method, electromagnetic power is fed directly to the radiating element or the radiating patch through a transmission line. That is your contacting method. That means there is a physical connection between the feed and the radiating patch. Okay, the second one is your non-contacting method. In the non-contacting method, electromagnetic power is fed to the radiating patch with the process of electromagnetic coupling. That means there is no physical contact between the radiating patch and the feed. Okay, the following four methods are used to energize the microstrip antenna. The first one is your strip line feed. Second one is your coaxial feed. Third one is your aperture coupled feed. Fourth one is your proximity coupled feed. Okay, the methods A and B fall under the contacting method category, while the methods C and D fall under the category of non-contacting method. Okay. Next slide, madam. Thank you. Now coming to the first method, that is your strip line feed. Now this is the diagram for the strip line feed. Now if you can see the radiating patch in the yellow color, that is a rectangle. Now to that you are feeding the electromagnetic power through the transmission line there. Now this transmission line is what is called as your strip line feed. Okay. Now the strip line feed is also called as your microstrip feed. Okay, now if you can see here, there is a direct physical connection between the feed and the radiating patch. Okay, in a few of the antenna researchers try to use a quarter wave transformer between the microstrip feed and the radiating patch. Now, why some of the antenna researchers do this is to get a good impedance match between the impedance of your microstrip feed and the impedance of the radiating patch. That is the general objectivity of your objective of the quarter wave transformer. Okay, it is used to match the impedance of the microstrip feed and the impedance of the radiating patch. Okay, now second advantage of this method is that it provides a planar arrangement. Okay, why this planar arrangement is obtained is because if you can see that the microstrip feed, the quarter wave transformer and the radiating patch all lie in the same plane. Okay. The disadvantage of this method is that it provides very low amount of bandwidth. Okay. Other disadvantage of this previous slide. Other disadvantage of this strip line feed is that as the width of the radiating patch increases, extraneous radiation can occur there, which can limit the bandwidth. Okay, next slide, madam. Okay, next method is your coaxial feed. Here the radiating patch is fed with the help of a coaxial or a probe feed. Okay, where the probe is directly kept on the radiating patch. Okay, now everybody might be knowing what is a coaxial cable. Okay, inside a coaxial cable, you will be having two types of cables. First one is your inner conductor, second one is your outer conductor. Okay, now what is done in this coaxial feeding mechanism is the inner conductor of the coaxial cable is connected to the radiating patch, and the outer conductor of the coaxial cable is connected to the ground plane. Okay. The advantage of this probe feed method is that the probe can be positioned anywhere on the radiating patch to get a good impedance match. Okay. The disadvantages of this method is that it produces very narrow bandwidth and it is difficult to fabricate. Why this probe coaxial feed is difficult to fabricate? Because a hole or a hole has to be drilled right all the way from patch to the ground plane. So that is a very tedious process, and sometimes that hole can come out of the ground plane below. Okay, so that the planar arrangement can be disturbed. Those are the disadvantages. Next slide, madam. Okay. Now third method is here, aperture coupled feed. Okay. Now in this method, two dielectric substrates are placed on top of each other. Okay. If you can see here in the figure 6, two dielectrics are placed on top of each other. Okay. Now how do you feed the power to the radiating patches? Now a slot or an aperture. Okay. What is a slot or an aperture is nothing but a hole. Okay, that slot or aperture is etched in the ground plane of the substrate 2 here. Okay, all the way to the radiating patch, which is placed on top of the dielectric substrate 1 there. Okay, now if you can see here, there is no where connection between the now electromagnetic power is transferred from substrate 2 to radiating patch through that slot there, through the process of electromagnetic coupling. So this method falls under the category of non-contacting method, where there is no physical contact between the feed and the radiating patch. Okay. Now the amount of electromagnetic power that is transferred to the radiating patch depends upon those dimensions of the slot or the aperture that is etched in the ground plane. Okay. Now, what is the other advantage of this method is that extraneous or spurious radiation can be minimized. Okay. Next slide, madam. Fourth method is your proximity coupled feed. Now here again you are trying to keep one dielectric substrate on top of other dielectric substrate. Okay. Now you are trying to feed the power to this method in between the two dielectric substrates. Okay, if you can see that dotted line there, that dotted line represents the in between the two dielectric substrates. Okay, so if you try to feed there, that feed is almost very much nearer to the radiating patch there. So that nearness is what is designated here as proximity coupled. Okay, nearness of the feed to the radiating patch through the process of electromagnetic radiation is what is called as your proximity coupled feed. Proximity is nothing but nearness. Okay, this advantage of this method is it provides high amount of bandwidth and limits extraneous radiation or spurious radiation. But disadvantage of this method is that alignment of the two dielectric substrates is difficult there. Okay, next slide, madam. Okay. Now coming to the radiation mechanism of a microstrip antenna. Okay, now this is your general structure of your microstrip antenna. Okay, now here the if you can see the thickness of the dielectric substrate here H. Okay, now this dielectric substrate thickness H is very much lesser than the wavelength at which the microstrip antenna operates. Okay, microstrip antennas are generally operated in the gigahertz range. Okay, greater than 1 gigahertz. Hence, these microstrip antennas are also called as their microwave antennas also. Okay, when you try to assume that the thickness of the dielectric substrate is very much lesser than the wavelength than the operating wavelength, okay, you can assume that there are no radiation along the height of the substrate there. Okay, and also assume that there are no radiations along the width of the dielectric substrate. Okay, if you try to assume that, you can plot the electromagnetic waves along the path as shown in the figure. Okay. Now, after you do that, next slide, madam. Okay. Now try to resolve those electromagnetic waves into two components. That is, one that is normal to the ground plane and one that is parallel to the ground plane. Okay, whenever you try to resolve along the normal components are always in phase and the parallel components are out of phase. And the normal components add up and the parallel components cancel each other. Okay, and okay, next slide, madam. Okay. Now coming to the advantages and disadvantages of your microstrip antenna. Okay, first one is here, they can be easily integrated with other electrical devices. They possess very small weight, they are small size and they possess low volume. They possess planar structure and they can be fabricated at very low cost, and moreover they can be also be easily fabricated. They operate at gigahertz frequencies or your microwave frequencies where the traditional antennas cannot be operated. They can be easily printed on your printed circuit boards. Okay, next slide, madam. Okay, now coming to the disadvantages, these antennas have little low efficiency because of dielectric and conductor losses, and hence produce less amount of gain. They possess very narrow amount of bandwidth. The bandwidth of the microstrip antennas generally lie between 2 to 5%. Okay. Other thing is, a few surface waves can be emanated in the dielectric substrate, which can lead to severe levels of interference. Okay. Fourth one is radiation in half space. Okay, you can see in the explanation of a radiation mechanism of microstrip antenna, radiation is happening only in the upper hemisphere. Okay, so the lower hemisphere is wasted. So hence the disadvantage is that radiation is happening only in the half space. Okay, some radiation can also occur from the junctions and fields. Next slide, madam. Okay, now coming to the applications, they can be used in satellite communications for various TV broadcasts. They can be used in remote sensing, wireless communications like your GSM, GPS, pagers, etc. They can be used in various internet services like Wi-Fi, WLAN. Okay, and they can be used in microwave and radar communication. Microstrip antennas major thrust area is in your microwaves and radar engineering. It can be used for various manufacturing of various radar antennas, phased array antennas, etc. And they can be used in various medical applications for the treatment of tumors. Okay, next slide, madam. Okay, now this is your microwave frequency spectrum. Okay, these microstrip antennas are used for frequencies greater than 1 gigahertz. This frequency band is very important. Like L band ranges from 1 to 2 gigahertz, S is from 2 to 4 gigahertz, C is from 4 to 8 gigahertz, X band is in your 8 to 12.5 gigahertz. If you can see the X band, many people might be using in your microwave lab in your final year electronics and communications engineering. Okay, X band is the one that you use in your frequency meters. That band is your 8 to 12.5 gigahertz. Okay, KU band is 12.5 to 18 gigahertz. K band is 18 to 26.5 gigahertz, followed by the KA, and millimeter band is greater than 40 gigahertz. Okay, next slide, madam. Okay, now coming to microstrip antenna array. Okay, everybody might be knowing what is an array. An array is defined as a arrangement of similar elements in a particular fashion. Okay, that particular elements can arrangement can be either in linear, circular, planar, elliptical, etc. Okay. Other thing important point to be noted is that all the performance parameters of microstrip antenna are applicable to microstrip antenna array, okay, which I'll be discussing later. Okay, and these microstrip antenna arrays can be broadside or end fire. Okay, broadside is the one where the radiation is perpendicular to the arrangement of the antenna array. End fire is the one which is parallel to the arrangement of the antenna elements. Okay, now coming to the feeding mechanisms of microstrip antenna arrays. Microstrip antenna arrays can be energized using two methods. First one is your series method and second one is your corporate feeding method. In the series feeding method, okay, all antenna elements can be are arranged linearly, and the feed is first energized, and the antenna array is energized only at the first element. Okay, and all the antenna elements are joined with the help of a quarter wave transformers. Okay, and this feeding mechanism produces reduced feed length and reduced losses, but disadvantage of this method is that it produces narrow bandwidth. Okay, next slide, man. Thank you. Second method is your corporate feeding method. In the corporate feeding method, power is provided in the form of power splits of n is equal to 1, 2, 4, etc. Like here the number of elements are 8. Like you can use a corporate feeding method for feeding elements in even numbers, like your 2, 4, 8, 16, 32, etc. Okay. Advantage of this method is that equal power is distributed to the all the elements, which is not unlike in the series feeding method. Okay, the advantage of this method is that it provides wider bandwidth than the series feeding method. Okay, next slide, man. Now coming to the latter half of the talk, that is your scattering parameters. Okay, scattering parameters are the parameters that are used for the analysis of the any circuit, any microwave circuit. Okay, now these scattering parameters are also called as your S parameters. Okay, they play a very important role in micro and RF systems. Now try to consider this figure 12 here. Okay, it is a two-port network where A1 is the input power and A2 B2 is the power forward power that is going into the port 2, and B1 is the output power, the reversed power. Okay, if you try to represent the scattering parameters in the form of a matrix, you will get it as B1 B2 is equal to S11 S12 S11 S12 S21 and S22 followed by A1 A2. Next slide, madam. Okay, now coming to the four parameters here. First you take the parameter S11. S11 now can be defined as B1 upon A1, where the A2 is equal to 0. That means it is the ratio of reflected power upon input power when the A2 is equal to 0. A2 equal to 0 means the output circuit is output terminals are open circuited. Okay, so you can designate S11 as reflected power upon incident power. So reflected power upon incident power is nothing but your reflected power. Okay, that you can call it as reflected loss. Okay, S11 is also called as return loss. Okay, if you now take S21, that is the ratio of B2 upon A1 for A2 equal to 0. That is transmitted power 2 upon incident power 1. So you can say S21 is your transmission coefficient. S11 is your reflection coefficient, S21 is your transmission coefficient. Okay. Now coming to the S22, that is B2 upon A2 when A1 is equal to 0, that is reflected power at 2 by upon incident power at port 2. So S22 can now be taken as reflection return loss or the reflected loss at port 2. Now coming to the fourth parameter S12, S12 is B1 upon A2 when A1 equal to 0 there. That is reflected power at port 1 upon incident power at port 2. So S12 is called as your transmission coefficient. So please try to remember S11 and S22 represent the reflection coefficients or return loss. S21 and S12 represent the transmission coefficients. Okay, other important point to be noted is that another important point to be noted is that whenever in the S parameter notification, if you try to say Sij, okay, Sij, always the first digit designates the output port, the next digit designates the input port. Okay, let's say I put it as S23. That means the output port is port 2 and input port is port 3. Okay, now coming to the properties of scattering parameters. A scattering matrix is always a square matrix of order n by n. It can be 2 by 2 or 3 by 3 or 4 by 4. Okay, scattering matrix is a symmetric matrix where the magnitudes of Sij are equal to Sji. That is, magnitude of S12 is equal to magnitude of S21. Okay. Third property is scattering matrix is a unitary matrix. Fourth property is the sum of the products of each term of any row or column multiplied by the complex conjugate of the corresponding terms of any row or column is 0. Okay. Next slide, madam. Now coming to the performance parameters of microstrip antennas. Now these are the performance parameters. First one is your lower frequency, next is higher frequency, next is return loss, next is resonant frequency, next is bandwidth and bandwidth in percentage, next is mutual coupling, last one is your virtual size reduction. Next slide, madam. Now coming to the return loss. Return loss is nothing but the defined as the amount of power that is returned back to the antenna. Okay, this is designated with the scattering parameters S11, S22, S33, so on. Okay, now the unit of return loss is dB. Okay, now I'll come back to this graph later, madam. Next slide. Now coming to the lower frequency. Lower frequency is defined as a frequency where the return loss or the reflection coefficient crosses the minus 10 dB for the first time for a band of frequency. Okay, unit is hertz. Madam, please go to the previous slide. Now if you can see here, the return loss is designated with the green graph here. Okay, here it is written as measured S11 with the green line. Okay, if you can see here, it is touching a minus 10 dB line at 2 points. First here, second time at a higher value. Lower frequency is the one where the return loss graph crosses the minus 10 dB value for the first time for a band of frequencies. Okay. Now upper frequency you define as a frequency where the return loss graph crosses the minus 10 dB value for the second time for the same band of frequencies. Okay, if you take this band of frequencies here, the green one, it is crossing for the first time here and second time at the second time. So the lower frequency is the first one and the higher frequency is the second one. Okay, next slide, madam. Now, how do you define a resonant frequency? Okay, resonant frequency is defined as the frequency where the antenna produces least amount of return loss in between the lower and upper frequencies. Okay. Now please go to the previous slide, madam. Okay, now coming to how do you define the resonant frequency? I have defined resonant frequency as the frequency where the uh, 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 amount of return loss is least or minimum in between the lower and upper frequencies. So if you can see here, the green graph is slightly going down in between the lower and upper frequencies. Okay, where it is touching the least value, approximately minus 21 dB. Okay, so that frequency is your resonant frequency. Okay, so the resonant frequency in this case is approximately 5.5 gigahertz, and the return loss is minus 21 dB approximately. That is how you define the resonant frequency and return loss. Okay, next slide, madam. Next, bandwidth is defined as the difference between the upper and lower frequencies for a particular band of frequencies. Okay, bandwidth in percentage is calculated by using this following equation 1, where is bandwidth upon resonant frequency into 100%. Okay, bandwidth you get it by subtracting the lower frequency from the upper frequency. Resonant frequency you can get it from the graph there. So you can get the value of your bandwidth in percentage. Next slide, madam. Okay. Now other important parameter is your mutual coupling. Mutual coupling is parameter you generally arise in the case of microstrip antenna arrays. Now in the case of antenna arrays, you can have more than one element. Okay, so whenever one element is trying to transmit or receive electromagnetic waves, and when the other element is trying to receive those electromagnetic waves, there can be certain amount of interference. Okay, that interference levels you can designate using this mutual coupling parameter. Okay, mutual coupling parameters are always designated by the transmission coefficients. Okay, transmission coefficients are designated by the scattering parameters S21, S12, S31, S41. Okay. Now, for example, madam, please go to figure number 13, madam. Thank you. Now, if you can see in this graph, the return loss plot and the mutual coupling graph, okay, are overlapping each other at the resonant frequency. Okay, please participants, please try to understand this very carefully. If you can see in this figure 13, graph of S parameters versus frequency, the plot of resonant return loss is designated with green color, and the mutual coupling graph is designated with red color. That is a measured one. If you can see at the resonant frequency, they are overlapping with each other. Whenever the return loss plot and the mutual coupling plot are overlapping with each other, it implies that there is huge amount of interference between the transmitting and the receiving antennas. Okay, please try to understand. Whenever there is the plots of return loss and the mutual coupling graphs are overlapping with each other at the resonant frequency, okay, it implies that there is huge amount of interference between the transmitting and the receiving antennas of that particular microstrip antenna array. Okay, whenever there is interference between the two elements of an antenna array, okay, information or the data cannot be transmitted easily or accurately or reliably between the two elements. So that is the importance of your mutual coupling parameter. Now going to next slide, madam. This one. Now if you see figure 14, madam. Thank you. Now if you can see in this graph, if you can what you are observing in this graph is at the resonant frequency of 5.5 gigahertz, okay, the return loss plot, which is designated in green color, and the mutual coupling graph designated in red color are no more overlapping, okay, which implies that there is reduced amount of interference level for this microstrip antenna array compared to the previous microstrip antenna array. So whenever the graphs of return loss and mutual coupling are no more overlapping with each other, it implies that interference levels are minimized, and information or the data can be easily transmitted between the antenna elements of that microstrip antenna array. This is a very important parameter for the analysis of your microstrip antenna arrays. Okay, next slide. Okay, next, last is your radiation pattern. Okay, in the radiation pattern, this radiation pattern can be plotted on a polar plot, or even you can plot it in a normal graphs also. Okay, this radiation pattern shows the variation of electromagnetic power along 0 degrees all the way through 360 degrees. Okay, you can plot electromagnetic power at various angles like 0 degrees, 90 degrees, 180 degrees, 270 degrees. Okay, now how do you calculate? You can calculate three parameters from the radiation pattern. First one is your front power. Front power can be calculated at the angle of 90 degrees. That means how much power, electromagnetic power, is being radiated at the angle of 90 degrees. That designates your front power. Okay, next parameter is your backward power. Backward power is also called as your backlobe radiation. Okay, backlobe radiation is the power that is radiated at the angle of 270 degrees. Okay, so here approximately it is minus 4 dB is your forward power, and the backward power is approximately somewhere around minus 12 dB. That I have plotted for two different antennas here. Okay. The other parameter that can be calculated is the front to back ratio. Front to back ratio you can calculate by subtracting the backward power from the forward power. Okay, all the forward, backward, and the front to back ratio can be units are in terms of dBs. Next slide. Next slide. Now coming to the conclusion, these microstrip antennas are very prolific antennas, and study of their basic parameters and basic understanding and basic structure is very much necessary or requisite for the proper understanding of their role in the research. The antenna research, people who are practicing research in antenna engineering or micro engineering or radar engineering, they have found a very amiable candidate in the form of these microstrip antennas to design different types of designs of these microstrip antennas, and they have produced novel microstrip antennas. Next slide, ma'am. Any questions from the audience?
The session is now open for discussion. Candidates can post their comments to witness. There's a question, sir, whenever you're ready. Sir, there's a question. Whenever you're ready, I can read it out.
Yeah, you can read it out.
There's a question from Arun. When we are using DGS more radiation backlobe, he's asking how to avoid this.
Okay, madam. You can decrease the backlobe radiation by using electromagnetic band gap structures. Okay, in my research work, I have used the combination of DGS and electromagnetic band gap structures. Initially, when I've used DGS structures in the microstrip antenna arrays, okay, I got huge amount of backlobe radiation compared to the conventional antennas. But after I've incorporated the EBG structures, that is the short form of your electromagnetic band gap structures, the backlobe radiation can be reduced considerably. Okay, and other thing you can also reduce backlobe radiation is you can also use nanotechnology in microstrip antenna arrays. That method also I have done in my research. Like you can use a silver deposition on top of the radiating patch as well as in the ground plane, and after you simulate and take the measurements using the vector network analyzer, you can experience that reduction in backlobe radiation.
So there's another question.
Yeah, sure.
Circular polarization tech for microstrip antenna.
Can you repeat the question, madam?
Circular polarization tech for microstrip antenna.
Circular polarization techniques. Okay,
Yeah.
okay, techniques.
Yeah, for the tech.
Those things I'm not sure, madam, because I have not measured polarization in my this thing antenna arrays. Maybe I guess you can use shorting pins for the circular polarization, but I'm not sure. But if you want me to get back to you after I do some research on circular polarization, I can get back to you.
Hope the answer is clear for time. We are still waiting for some more questions.
Hello, madam.
Yes, sir, we are still waiting for some questions.
No, madam. I just forgot one small point. I'll just discuss it, madam.
Sure, sir.
Just go to figure 1, madam, in the presentation.
Okay.
Next slide. Next slide. Next slide, madam.
So is it figure 1 that you asked for?
Sorry, madam. Figure 2, madam. Sorry.
Okay.
Sorry, participants. I forgot a small point to be mentioned. Okay, dielectric substrate is has two important parameters. First one is your dielectric constant. Second one is your loss tangent. Okay, dielectric constant is also called as your dielectric permittivity. Permittivity of the dielectric substrate. Okay, you can use different types of dielectrics, like you can use FR4 glass epoxy, you can use RT diorite, etc. Okay, it is two important parameters which I forgot to mention in my talk. First one is your dielectric substrate. Second one is your loss tangent. Okay, those things. Thank you.
So there's another question.
Yeah, sure.
They're asking for an explanation about the permeability.
Permeability you'll experience in magnetic materials, like okay, dielectrics are always have these parameters, that is your permittivity. Okay, permeability is what is experienced in your magnetic materials, like Okay, represented with mu, symbol mu.
Thank you, sir.
Yeah. Again, you can have three types of magnetic materials like paramagnetic, ferromagnetic, these things like mu are greater than one, those things like.
Hello, sir. Hello.
Hello. Yeah, please tell.
Sir, permittivity is nothing but how much that electric field is withstand that material. This is permittivity, na, sir.
A dielectric substrate is characterized with permittivity, epsilon r.
Yes, sir. Based on epsilon r value only, that the material will withstand that how much electric field.
Yeah.
Like that, what is meant by permeability, sir? Permittivity, I understand.
Permeability. Even I am not sure, sir. Like, but I'll remember your question. I'll get back to you, sir.
Okay, sir. Thank you, sir.
Thank you. Your good name, sir?
Arun Rai, sir.
Arun. Okay.
Okay,
Yeah.
sir.
I'll take your WhatsApp number and I'll give a response to you.
Oh, okay, sir.
Okay. Thank you.
Okay.
Sorry to interrupt, sir. I guess you can share your email ID.
Sure.
Participants,
Yeah. I'll share it, madam.
questions. Thank you.
Yeah. Can I share it in the WhatsApp, madam?
Yes.
Yeah.
Sure.
Yeah. Sure.
So you can even do it in the comment section if you're able.
Okay. I'll do it just now.
Just still waiting for some more questions,
Yeah.
or else we can just close.
Miss Shalini?
Yeah.
Yeah. We can post the feedback form meanwhile. And sir,
Yeah,
can-
sure.
Yeah, okay.
Thank you, sir.
Madam, I have shared that email ID, madam.
Sure, sir. So it's
Yeah.
visible. Participants can please make note of the email ID as well as the feedback form. The link has been posted. And if there aren't any more questions, I hope we can close the day. And on behalf of brand publishers, I take this opportunity to thank our resource person for the time and effort taken to prepare the presentation and for conveying his best acquired knowledge on microstrip antennas and scattering parameters. Hope our participants found this session useful, and I would like to thank you all for making this event a success. If you find our webinar events useful, kindly share a word with your friends and do participate in our future events as well. Please don't forget to subscribe to our YouTube channel and check out on our official website as well. Signing off for now, this is El Shalini, wishing you all a happy weekend. And thank you so much, sir, for joining with us today and for
thank you.
delivering this wonderful session. Thank you so
Thank you.
much, all our
Thank you.
participants.
Thank you.